Let's get started. So, hello everyone. Oh, the sun just came out. Hope you're all well, hope you're all safe. The test is on Thursday. That was just a very insidious joke that Ash came up with. Yeah, I don't know. This is why you guys need to read your emails. Okay, so I already told you guys the test is on Thursday. Test is on Thursday. And it's funny how some people got in on the joke and like, yeah, it's already like, why you guys messing with your brothers and sisters like that? Okay, like you shouldn't encourage. Okay, so test is on Thursday. I knew that some people were having issues logging into the thing, getting it to run and all that. And so, did I actually do it already? I probably did it for the other section. What I want to do is I'm going to open the mock test again. So if you already did it and you already submitted your answers, you don't need to worry about this. It's just for people who were having issues who didn't actually get to try it before it closed down. I want to open it again so that you guys can try to get in, fix whatever issues. Pretty much from what it seems like, you need to have like everything perfect for like any little thing. The program is very finicky. So if your computer's like low on memory, if you don't have like 2 gigabytes of memory to spare, it doesn't like that. If your webcam, if there's anything wrong with it, it doesn't like it. So like if there's anything wrong with your system, the Proctorio thing really gives you a hard time to log in. So I know some people have been having a hard time to log in. So what I'll do, I'll open it again. I will leave it open until, yeah, maybe Thursday at noon. But you probably should try to get your responses in like way before that. So if I open it again, I'll open it again tonight. If I didn't already do it, I'll definitely do it after class. I'll open it again tonight, and it'll probably be good if you actually try to get through it tonight. So yeah, that's good. I don't think it works on tablets. And once you upload the system, it will give you instructions on what it wants. I don't think it watches your hands the whole time, but it'll just it'll need your face or something like that. Anyway, yeah, just type done. Yes, you just type done. So that's just for me to track that you're moving through the exam okay. So it's not like a bunch of people just not answering problems. But your actual work that would be graded would be the scans that you send in. So yeah, practice going on the system, practice seeing the test, going through the test, then practice uploading your work after using the apps that I mentioned. I said in an email at some point, Scannable is probably the recommended app for iOS devices, and Genius Scan is the recommended device for Android devices. And so there'll be 2 separate things. There'll be a test, and then there'll be a submission link. The submission would technically be under the title homework, but it'll be titled test submission. And so you do the test, and then once you close the test, you go into the homework, and you can upload your scans. And it's really quick on the phone. I tested it myself on an Android, and it scans very well and all that good stuff. So yeah, that being said, the test is going to be very similar to the mock exam, not going to really change anything. I've given you guys 2 mock exams at this point, and you'll notice that they're very similar. And so I'm going to keep the actual exam very similar. That one is on Thursday during class time. And on Friday, I want to do an extra lecture. I'll probably talk about that a little bit. But yeah, I'll probably talk about that towards the end. Okay, let's just actually share the screen here. All right, so this is where we are. And as always, I am going to probably turn off the video just to reduce the amount of glitchiness. And then, yeah, let's actually begin. So yeah, I sent out an email. I think I already sent out an email telling you guys I would do this, but I want to reduce the amount of cramming that would happen just before the final, especially since it's an unprecedented kind of final. It's a very new type of final. And I'd like to, any information I get about that final, just give you guys moving forward in a timely manner, as timely as possible. So whenever I give you a test, so we're having a test this week and we're having a test 2-ish weeks from now. So when I'm giving those tests, I would like to do a makeup lecture. It's semi-optional. You should consider it mandatory if you can show up at all. But I'll send out like a doodle poll to just select all the time slots that you'll be able to show up. I'll pick the time slot that most people can show up, and we'll run an extra class. So just that we don't lose any time. I don't want to lose these 2 class days and then realize the last 2 days of the semester we have to really be cramming in a lot of things. Yeah, I'll send out that doodle poll. I started to create it and then it closed down, and then I have to create stuff. Okay, anyway, let's actually just jump into it because we have some interesting things to do today. Last time we found out that equations of lines weren't what we thought they were. So a lot of you, of course, know this thing that has been drilled into your, oh, y equals mx plus b, the equation of a line. We found that y equals mx plus b, once you go in higher dimensions, it's no longer the equation of a line. It is actually the equation of a plane. We looked specifically at what the equation of a line would look like. We determined it using vectors. So you can talk about a vector form of the equation of a line. What you need is a point and a direction that is parallel to the line, and you will be able to create the equation of the line. This is the vector form. If you set x equals the x coordinate, y equals the y coordinate, z equals the z coordinate, you get the parametric form. And then you can get something that's called the symmetric form, which is more of like a scalar form of the equation of the line. But the vector is very efficient. What's nice about a definition like this, specifically this definition, this version of the definition, is that no matter what dimension you are in, that is going to be the guide. A line will look like that. So now some of you might have been like, what? Y equals mx plus b is not the equation of a line? You'll never have that kind of situation again. You won't go into dimension 6 and realize, what we learned in Calc 3 is not the dimension of the equation of a line anymore. That's not going to happen. The vector equation form of the equation of a line will work in all dimensions. This is why we kind of like vectors. It's really nice to describe things, especially in multiple dimensions. The only thing you have to do when you change a dimension, you add a coordinate. That's it. We don't have to totally revamp everything and look at everything from a different point of view. So one of the reasons why learning about 3 dimensions is really important, and this is what Calc 3 will go a lot more into, is that once you really learn about 3 dimensions and you learn all the intricacies, it's very easy to generalize that to higher dimensions. 2 dimensions, what you've been doing in Calc 1 and algebra and pre-calc, that is its own kind of beast, and you spend a long time with it, but now we want to go to higher dimensions. So this is how we look at the equation of a line in higher dimensions. And we did some examples where we found the equations of lines. So you need to know these equations, this one and this one specifically. This one I threw in for completeness, but your textbook actually doesn't even mention this one. The textbook that we had for this class before the one that you currently have mentions this one. So I just decided to throw it in there. But the vector form and the parametric form, you definitely need to know those equations of a line. Okay. And you need to know how to use them. So given certain pieces of information, you should be able to piece together a line. So for example, if I give you a point and the direction vector, you should be able to find a line. If I give you 2 points, you should be able to find a line, etc. And we did a bunch of examples there. And what we want to do now is talk about another situation. So remember in 2-space, when you were in R2, if you had two lines, there were three situations. The lines could be parallel and never touch each other, or the lines could touch each other at one point, or you could have actually, the lines are actually the same line and they are right on top of each other. Okay, so that's one line. Here's another line. Here's another line. And those represented all possibilities. Either you're parallel and you never touched, or you're parallel and you always touched, or you intersected at a single point. It turns out in higher dimensions, there are other possibilities. It is possible for you to not be parallel and at the same time not touch at all. So this is what we call skew. So that's the term we use here. And we will, oh, I see a question here about the final percentage. I'll talk about that. That's still in the works. So different professors and different courses are, the course supervisor for each course is working on how the grading breakdown is going to work. So again, when I hear about that for us, I'll let you guys know. Okay, moving forward. When a line is skew, it means it is not parallel and it's not intersecting. Okay, and so there's a whole other scenario. So in R3, in R3, an additional situation. Right? You can be in 3 space and you can have one line doing its thing, and then you can have another line that is in a different direction. And it's like, it's not parallel and it doesn't actually touch the other line. Like this green one here moves under the black one. And that's called skew when everything do that. And you need to be able to identify when these properties are there. So let's actually just jump in. We know how to talk about the equations of lines here. So let's write this one in vector form just to be a little bit nicer. So this is x, y, z equals the coordinates without the t's. That's actually, you can think of that as a point the line passes through. And the coefficients of t's give you the direction vector. Okay, so that's the equation of line 1 in vector form. That should be a 6. And here is the equation of line 2 in vector form. So this is 10, 3, 7, plus s is the parameter here. And this is minus 6, 4, 8. All right, so what do you think? Are these guys parallel or not parallel? Okay, that's for you guys. Parallel or not parallel? Parallel, how do you know? Right, so one, their direction vectors, if I look at, say, this guy and compare it to that guy, this tells you about the directions of the lines. And it turns out that the green one, if you multiply the green one by 2, you actually get the other one. So one vector here, you see, is a scalar multiple of another vector. This guy is a scalar multiple of that guy. So this means their direction vectors are parallel, which means that the lines themselves are parallel. So these are two parallel lines, right? So this question, determine whether lines are parallel, intersecting, or skew. So first try to see if they're parallel or not, and these ones are parallel. So this is version A. If they're not parallel, try to see, do they intersect at some point? or are they completely skew? So let's actually look at this example right here. Okay, so here's example B. Let's rewrite these guys again. So here, this is x, y, z equals, coordinate is 2, 3, 1 plus t times 4, 0, minus 1. And the second line, it passes through the point 2, 3, 1, and its direction is 2, 2, 1. Okay, parallel. Right, so not parallel. You can see because, is this thing working? This thing is. Let me relaunch OneNote here. Okay. Started spazzing out. Okay, so boom, boom, boom. How do you know it's not parallel? Well, if you look at this here, it says 0. If you took a scalar multiple of this guy, it'll always be 0. So this guy here is not 0. And that automatically tells you it's not parallel, because any scalar multiple of 0 should give you 0 in that coordinate. So now let's answer the question. Do they intersect? And it seems like someone believes that they do. So how do you know that they intersect? What would you want to do to show that they intersect, if they do? Right, you compare the x, y, and z coordinates, and the idea is, are the x, y, z coordinates, someone just entered, the same values at some point? So in other words, I want the x coordinate of line 1. I want to compare that to the x coordinate of line 2. So in other words, does the following have a solution? Is the question that you should be asking. So the first one, your x is actually 4t plus 2, and then so you want to know, does 4t plus 2 ever give you the same result as 2s plus 2? And at the same time, does the y value 3 in the first guy, would he be at the same time equal to the y value of the second guy? And does the z value of the third guy, is that equal to the z value of the second guy at any given point? So you want to know, does this system actually have a solution? Can I find values t and s that will make all of these true at the same time? And so what do is you have 2 equations and 3 unknowns, so you have more equations. What you do is you just use 2 equations at a time. So for example, we can use 4t minus 2s is equal to 0. And in equation 2, I can use, say, 2s plus 3 equals 0. Now, right away from this, I can see that my s is equal to minus 3 halves. Plug in 1, and then so it's 4t minus 2 minus 3 halves equals 0. So then I would have 4t plus 3 equals 0. This means that my t is equal to minus 3/4. And now you want to check in the third equation. Does that actually work out? Check in equation 3. So you go to equation 3. This is minus t plus 1. So minus t plus 1 would be equal to positive 3 over 4 plus 1, which is 7 over 4. Whereas your s plus 1, that would be minus, where is s? Minus 0 over 2 plus 1. Right. This is there's a 3 on this side. It wasn't 0. There's a 3 on this side, which means that that's a 0. And which means that's a 0. Which means that your t would be 0. Okay. So Muhammad fallen asleep at the wheel here. Let us down the wrong path. He's out here trying to convince everyone that we have a test today. This is t equals 0. And we can check your minus t plus 1 in this case would be 0 plus 1, which is 1. And your s plus 1 would be equal to 0 plus 1, which is 1. And so, yes, they intersect. Specifically, at, and I can use either one of these lines and just plug in one of these guys equal to 0. So plug in t equals 0, that's 2, 3, 1. Now, of course, this answer was almost obvious from the beginning. We kind of saw it right here. They both had the points 2, 3, 1. And so by making these guys equal to 0, notice that we could pass through that point. It's not always that obvious, but in this example, it was obvious. I just want you guys to see what the calculations actually look like, what you'd have to do. If you realize it's not parallel, then what you want to do is you want to set all the coordinates equal to each other and try to find a solution. You can do that by solving 2 equations at once and then checking that those solutions work in the third equation. Now, if all these 3 equations work out, then yes, they do intersect, and they intersect at the points given by these parameters. So you can either plug this one into the second line or that one into the first line, and you will get the coordinates popping up. So hopefully that is clear. Okay, let's move on to the last example, which you guys can probably tell is going to be the guy that does neither. Okay, so C, L1. So this is X, Y, Z. Someone else coming in. X, Y, Z equals 0, 2, minus 1 plus T times 3 minus 1, 1. And your L2 1, minus 2, minus 3 plus S times 4 minus 2 4, the coefficient of S is 1, and the coefficient of S here is minus 3. So again, not parallel. And you can automatically see that again, just find kind of one thing where you can connect. To go from a minus 1 to a plus 1, your scalar would have to be -1. You'd have to multiply this by -1. But clearly 4 is not -1 times 3. So the middle, I just find a coordinate where I try to figure out the scalar relationship between them and just see, are all the other numbers following the same scalar relationship? In this case, it does not. So now we want to check, do they intersect? And so I'm going to set 3t equals to 1 plus 4s. Then I'm going to set 2 minus t equals to s minus 2. Then I'm going to get t minus 1 set equal to minus 3s. And now we know how to actually tackle this. We would solve, so in equation 1, 3t minus 4s equals 1. In equation 2, I can have t plus s. I move the t over here, and the 2 over here equals 4. And what I can do here is do something like multiply the second equation by 4. This is equation 2 times 4. And then add it to equation 1. The s's would die. Then I would have 7t is equal to 17, which means that your t is 17 over 7. So that's one solution. Then I use either one of these. Now I know that my t plus s is equal to 4. This means that my s should be 4 minus 17 over 7. 4 is, I want to say 28 over 7. And if you want to know one of the things that makes me sleepy even when I'm supposed to be wide awake, it's arithmetic. Like I hate arithmetic so much. It's so boring. Okay, 28 minus 17. You have to minus 7, you get 21, then you minus 1. I guess that's 11 over 7. So that would be my s value. And so now you just check in equation 3. The equation 3 says that t minus 1, which is equal to 17 over 7 minus 1. 1 is 7 over 7, so this here is 10 over 7. And then you look at it, minus 3s. So here you look at minus 3s. This is minus 3 times 11 over 7. It's going to be minus 3 minus 33 over 7. That's minus 21 over 7. But I think clearly here, this is not going to work out because that's a negative number. So not the same. And so not parallel, not intersecting. That leaves us with one other option. The lines are skew. Okay. All right, so that's with lines. We know the equations. Now we know how two lines can interact with each other. They can be intersecting. This intersection includes being parallel. Parallel lines intersect automatically. But it's possible for them to not intersect, for them to not be parallel, but they intersect at one point, like this one. It's also possible for them to not be parallel and at the same time never intersect. So in this situation here, again, it's like you have one line, he's doing his thing over here, and then you have another line doing its thing, but it's actually going below that line. Like they're in totally like different scenarios. So it turns out the kind of properties that you're used to, like this kind of property here, where there are only 3 scenarios and all that good stuff, turns out that that kind of property actually is true for planes in 3D. It's not true for lines. Yeah, but that's lines. That's everything I wanted to tell you guys about lines. So we know the equation. You need to know these two specifically. you can pretty much ignore the third. I don't see that coming up. And yeah, you should know how to find the equation of a line if someone describes all these properties of the line to you, like what are the points it passes through, etc. And you should be able to know, if given two lines, do they intersect? Are they parallel? Are they skew? Right. Now let's move on to the other part of the chapter, or the section, let's say, and that's planes. So the title of this section is Equations of Lines and Planes. So let's actually talk about planes. And these guys are actually loads of fun, a lot more fun than lines, at least I think so. But let's actually talk about the equation of a plane. So we know the equation of a line uses vectors, and we have the vector form. And we also know that y equals mx plus b is the equation of a plane in 3 space. How do you actually figure that out? How do you actually know what the equation of a plane is? So let's say here I have a plane. So here's my plane. Okay. Now let's give it some identifying characteristics. Now we know that the direction of a plane that matters, we saw this before, is the orthogonal direction. So let's suppose I know such a direction. Let's suppose I know the normal vector to this plane, call it ABC. And let's suppose I even know a point. Now the normal vector doesn't have to touch this point, the vectors can move around, but just to get the picture to be meaningful, let's pretend I have a point and I put it at the base of this normal vector here. That's a point x naught, y naught, z naught. So I also know a point in the plane. So I know a point and a normal direction, normal vector. So same way for a line, you need a point and a direction. You need the same thing for a plane, right? So for the line, you need a direction that is parallel to the plane, to the line. For the plane, you need a normal vector. So that's the only meaningful direction for a plane. And we explained why I used that whole book with the pens and, okay, yeah. So now let's say there's some other random point here, and let's make this point variable, x comma y comma z. What we want to do is we want to be able to describe this point. With an equation. That's the equation of a curve, by the way. Just some sort of relationship that all points in the curve obey. That's just what it is. So how would we go about actually doing this? Well, since I know this, I can actually connect it to any other point in the plane via a vector. And because the normal vector is normal to the plane, it is automatically normal to any vector that's in the plane. So that means that n and this vector, let's call it A, are orthogonal. And now is my question to you. So n and A are orthogonal. This means, so tell me, what does it mean for two vectors to be orthogonal? Two vectors are orthogonal. What's the kind of first thing you think about? Right, dot product is 0. Good. Okay, so we know this from the maxims. Don't forget that. The other class was kind of rusty on that. Where did I actually put that? Oh, I don't remember. I think it was over here. Yeah, so remember this thing here? Yeah, take a screenshot of that box. Very important. These are just things you should know off the top of your head, like right away. A and B are orthogonal if the dot product is 0. They're parallel if one is a scalar multiple of the other. They're also parallel if the cross product is the 0 vector. Another way to determine parallel is if the magnitude of the cross product is the 0 scalar. So remember that stuff. Okay, so orthogonal, you should know that means perpendicular, quote unquote, just in a more comprehensive sense. And what it means in an equation type sense is that the dot product is 0. But that actually means this vector, a comma b comma c, dot product with the vector a, which if we take the final minus initial point, that dot product is 0. And that leads us to the equation of the plane. Boom, right? This dot that must be equal to 0. This is called the vector equation of a plane. It's not really used though. This, boom. If you actually do the dot product, you expand this, you get this. This is the scalar equation of the plane. I would suggest you remember this. Now, this is a common one. This is the common equation used for construction. Okay, so that is the equation of a plane. So you'll also notice that y equals mx plus b will follow this sort of equation. If I plug in c equals 0, plug in b for y naught, plug in 1 here, plug in m here, plug in 0 here, you get y equals mx plus b. So that is the equation of a plane because it fits this guy. It will obey these rules. And so this is called the scalar equation. It's the most useful one. You should note though, you can actually expand this and write it in another form. But of course it's the same, just a different form of this guy. Right, you can just multiply out the parentheses and move the constant to the other side, and they call that d here. But again, this is the one you want to remember. Okay, so when it comes to the equation of lines, you want to remember the first two that I gave you, the vector equation and the parametric equation. When it comes to the equation of a plane, the one you want to remember is the scalar equation. But of course, you should have some notion or some idea of where it came from. It's just us dot producting a normal vector with a vector in the plane. And that's the kind of thing that you probably need to know for whatever this final we're going to have is going to look like, because that's the kind of thing that you could ask in a multiple choice setting to somehow kind of ascertain, do students understand that this equation came from a dot product? Anyway, let's talk about, make a quick note on sketching planes. We're going to look at a lot of sketching today. Relatively speaking, we'll even look at more next class. But wanted to learn how to sketch planes. Okay, so I wrote it out in words here, so I'll just tell you. So let's say we have a plane, we want to sketch it. Sketching is going to be important for a multitude of reasons, which we'll continue to talk about later on. But if you want to sketch a plane, there is actually a quick way to sketch a plane, provided it's not like parallel to one of the coordinate planes or something like that. So how you would do it is you would plug in 2 variables equals 0 at a time and solve for the third variable. Now, what does this accomplish? So when you're on the x-axis, you have to realize that the x-axis, all the coordinates on the x-axis have this form. It's like a blah, comma, 0, comma, 0. And the z-axis is 0, comma, 0, comma, blah. And the y-axis is 0, comma, blah, comma, 0, right? Where the blah numbers can be thrown in there. So whenever you have 2 variables equals 0 at the same time, but the other one potentially isn't 0, what it means is that you are on an axis somewhere. And so what you can do by doing, what you can figure out by doing this, plugging in 2 variables equals 0 at a time, is you can tell where the actual, the plane will cut an axis. So for example, if I set x equals 0 and y equals 0, this would mean that my z would be 2. And if I set y equals 0 and z equals 0, I don't know why I'm doing it in this order specifically, but you would get x equals 3. And if you set x equals 0 and z equals 0, you would get y equals 6. And what do you do with these numbers? So you can draw axes here. And if you look here, z equals 2. What you would do is you would go over here and you would plot 2. And then you'd have x equals 3. And you would go on the x-axis and you would plot 3. And then you see here that y equals 6. And you would go over here and you would plot 6. And then what you want to do now is you want to actually just connect the dots with a line. Each pair of dots. So connect this, boom, connect that, boom, connect that, boom. And so that is your plane. That's your plane right here. So this is the plane that's slicing through the first octant, and it slices at a slant that looks like that. That's described. So that's how you would sketch a plane or kind of envision a plane. And of course, it keeps going in all directions. It's just slanted this way. And one thing we do know is that the normal vector to this plane, right, is going to be the vector 2, 1, 3, based on the equation of the plane. The normal vector is the coefficients of x, y, and z. Okay, so that's how you could sketch a plane, just so you know. Now, two planes are parallel if their normal vectors are parallel. That should be clear, I think. So you have two planes parallel here. Then the normal vector of this one and the normal vector of that one will be pointing in the same direction. And we define the angle between two planes as the angle between their normal vectors. So let's say I have a plane here doing its thing, and then there's another plane slicing through it. Right? So if I wanted to somehow measure the angle between these two planes, like this theta right here, which is very important that we would know in some context, all I have to do is measure this normal vector, measure that normal vector, call it n1 and n2, then theta would be equal to the angle between n1 and n2. All right, so that is a plane. That's the introduction. This is its equation and what the pieces mean. And from now on, this is actually going to be something it's always been important, but now on it's going to be even more important. You want to memorize equations. You don't just want to just memorize the equation. You need to know specifically what each piece of the equation means. The A, the B, and the C are the normal vector. The x0, y0, z0 are the coordinates. Which represents a point in the plane. You can sketch a plane by plugging in two variables that equals 0 at the same time, and then solving for the third. This tells you where it hits an axis, and you can just connect those with the lines, and you can actually see what that looks like. Okay. These are just some things to note based on how planes behave. And now let's actually look at some problems. So I put some of the answers here just in case I got lazy and didn't want to write them out, but I actually did do all the examples for the other class, so we're going to do it for you. Okay, moving on. Let's actually practice using this equation here. All right, so let's find the equation of the plane that passes through the point 1, 2, 3 with normal vector blah. So here, and I'll take this one because, you know, it's the hardest one. Course, you know, because I got your back. Okay, so here n equals ABC. That is the 1, 2, 3, right? That is the point that not the 1, 2, 3. That the normal vector is here. That is the -1, 7, 4. So that's your ABC. Then what you want is your x0, y0, z0. And that is just a point in the plane, which here we know it's 1, 2, 3. So now you plug into this equation. And when you're just learning the equation, you write it down every time until you have it memorized. Equations of lines and equations of planes, you have to know them. You have to know them very well. In the same way that they drilled into your head that y equals mx plus b was the equation of a line, and they weren't telling you the whole truth. Yes, what I'm telling you now is going to be the whole truth. Like things will behave like this in 3 dimensions and higher. So for real now, you can know this to be the equation of a line and know this to be the equation of a plane, and the ideas are still going to hold true in vectors. So you really need to know these. So if I ask you, what is the equation of a plane? You need to be able to regurgitate this. And you also need to be able to tell me what the specific letters mean in the formula. If I ask you what the equation of a line is, you need to be able to regurgitate it. Now these two equations don't roll off the tongue like y equals mx plus b, but it's very important that you know them like off the top of your head right away nonetheless. And so now you just plug in these numbers. So this is going to be minus x minus 1 plus 7 y minus 2 plus 4 z minus 3 equals 0. And that is the equation of the line. And yes, I told you that you could multiply out and write in a different form, but unless a specific form is required, I wouldn't worry about it. Just plug in the numbers and leave it as is. That's the equation of this plane. Nothing else to write down here. And are there any questions on that, like what I did? Plug in anything? Okay, so someone is going to help me with this one over here. Okay, so that's going to be the answer, just so you know, so we can check our answer at the end. This answer is multiplied out and expanded, so we'll go the extra mile just for the sake of comparison. I picked this problem out of a textbook, and that was the answer in the back, so let's make sure that we can get that back. All right, ideas for finding the equation of a plane that contains these 2 points, 3 points, okay? So we're given a plane. And what I know is I know 3 points in the plane. I know that there's 1, 2, 3 in the plane. I know that there's 3, 2, 1 in the plane. And I know that there is -1, -2, 2 in the plane. All right. So given that we have a plane and we know 3 points in the plane. All right, Ash is coming up. Make 2 vectors using the 3 points. Sounds like a good idea to me. So I can create 1 vector here. Now, of course, I know what that is. That is going to be final minus initial. 3 minus 1. 2 minus 2. 1 minus 3. And I can create another vector here. And we know how to create those vectors. Final minus initial. -1, -1. -2, -2. And 2 minus 3. So we have those 2 vectors. All right, so now that I created those vectors, what do we do? We cross product, right? Now, why did we cross product? Well, the cross product is going to give us a vector that's orthogonal to the plane. We spoke about that before. Cross product gives you a vector that's orthogonal to both vectors at the same time. And the vectors here are both parallel to this plane. So this vector here is going to be parallel to the plane. Now, if I call this one A, if I call the red one A, and I call the green one B, then this is actually the vector A cross B. Okay, using the right-hand rule. The vector coming down would be -A cross B. Now, to be fair, either one you pick is fine. But let's just pick A cross B just because. What that's going to give us, that's going to give us our normal vector. Now, hopefully you remember how to find the cross product. It's the I, J, K. List the coordinates of A, then list the coordinates of B, then create a vector. Block out everyone in I's column and row. This times this, minus that times that. So that's 0, -8. Block out J's column and row, -2, minus 4. But of course, you take a negative of the inside, comma, block out everyone in this column of that row. That's minus 8, minus 0. So our normal vector is this guy. So it's minus 8, comma 6, comma minus 8. Now, that happens to be the guy that's orthogonal to these, and his length is the area of the parallelogram formed by these two vectors. Now, we don't particularly care about the magnitude of the normal vector, as long as we get something that's parallel to the normal vector. So here, what you can notice is that we can actually use anything parallel. Can use anything parallel. Including, I could just scale this if I wanted. I can just divide this by minus 2, for example. And use that instead if I wanted to. And so now what I'm going to say, we're going to set this up. So now using n equals ABC equals 4 minus 3, 4, and x naught, y naught. I don't like how that x looks. X naught, y naught, z naught equals, I'm going to go over here, pick one of these points. Now it does not matter who you pick. Let's just go with 1, 2, 3. Right? Want you to be aware, could pick any point. And now we just plug it into our formula. So we know that the equation of the plane is going to be 4x minus 1 minus 3 y minus 2 plus 4z minus 3 equals 0. So that's going to be the equation of the plane. Now, we can actually clean this up a bit. Let's actually multiply this out. So this is 4x minus 4 minus 3y plus 6 plus 4z minus 12. So this is 4x minus 3y plus 4z equals, so minus 4 minus 12, that's minus 16, plus 6, that's minus 10. Move it over, you get positive 10. So we have that answer, and yeah, that was the answer. So that is the equation of the plane that contains these 3 points. And again, you have some choice here. You can literally take anything to be n, because of course, when you plug it into this equation, you can scale this, multiply both sides of the equation by any constant, and the equation will still stay the same as long as you're not multiplying by 0. So any non-zero scalar of this guy can work. And again, any point in the plane you want to pick, you can do it. So even if I use this number over here, this vector, and I use this coordinate, once I actually multiply out and simplify, I'll still get back this same equation. Any questions so far on this? Yes. So if you got different vectors, yeah. So there are multitudes of ways you could have actually created vectors in another way. You could have done, like, here were the 3 points. You could have connected the vectors that way. The vectors would look different, but they'd still both be parallel. You would actually get a normal vector that's parallel to this one either way. And you can try it. Like, you can go backwards here. You can connect those two with vectors. You can connect these two with vectors, and it'll be fine. You'll still get the same n, or in the sense that you'll get something parallel to that n. So yeah, any vectors you want to create in the plane will work, and any variation on the normal vector will work in the sense that anything parallel is going to work, and then any point you pick in the plane, it'll work, right? So in the initial state, like once you just plug it into that general formula, you might have people having answers that look very different. But if you were to like multiply out and group things or anything like that, you'll find that everyone's answer will actually simplify to the same thing. It has to. It's how the cross product works and all that. Let's actually try another example. Let's see if we have any ideas on this one. Okay, here we have a plane that we know a point in the plane and a line in the plane. Okay, so find the equation of the plane that contains this point and that line. So here is the situation. We have plane doing its thing. I know there's a point in the plane. I also know that there's a line in the plane. Okay, I know specifically the point is 3, 5, -1. And I know specifically the line is x, y, z equals 4, -1, 0 plus t times -1, 2, -3. So I know that specifically, right? So right? So here is your plane. So it has a point and a line. Tell me about what you think we could do to find the equation of the plane. Input your own t value, what would that accomplish? So I plug in my t value. You'll get 2 points for 2 values of t. So you want 2 points. Why do you want 2 points? What is your idea? What are you trying to do? Do you want to create 2 points so you can use the same solution we had for 3 points? Yeah, it's that reminds me of a joke, but whatever. Yes, kind of reduce the situation to a previously solved problem. The mathematician way of doing it. So I know how to solve it for 3 points. So let's create 3 points so we can use it. This kind of reminds me about what if you teach a mathematician how to put out a fire, and then if something's, I'm going to butcher the joke if I try to say it, but you guys probably even know the joke that I'm thinking about, right? So it's like, why did you set it on fire? Well, I was reducing the problem to a previously known solution. Okay, never mind. Okay, so it turns out here that can work, but it's actually going too far. You don't actually need 3 points. 1 point is good enough. And here's why. So let's say I plug in t equals 0 just to make it easy on myself, and I get this 1 point over here. So this will be the point 4, -1, 0. Now I can create a vector from that point to this other point, right? I'll call that vector A. Now, the only reason why we needed a third point was just to connect the points to create a vector. However, we already know a vector that's going in this direction, right? That is actually the vector that's parallel to the line. So we actually know that vector already. It's -1, 2, -1, 2, -3. We actually know a vector moving in this direction already. So we don't actually need 2 points over here. We already have the vector that we would have created with another pair of points. So I just need 1 point on this line to create this vector, and I already have another vector moving in that direction, which is known here. And of course, the vector A is going to be, well, like final minus initial. Or I could even do A in the other direction if I wanted to. But whatever, let's do 3 - 4, 5 - a -1, and -1 - 0. So that's my vector A. And then I can do the same thing. So my n equals, let's call this other guy B. So that vector here, that's my vector B, -1, 2, -3. So my n is just going to be A cross B. So it's going to be I, J, K, -1, 6, -1, -1, 2, -3. -18 plus 2. This is +3 -1. This is -2 plus 6. So you have that. But it's equivalent to picking something like just dividing through by -2, let's say. It's equivalent to picking that. And so what I would do is just use a point. So we're using A, x minus x naught plus B, y minus y naught plus C, z minus z naught equals 0. And this here is my ABC. And then I'm going to use, let's use the given point just because. I can use any one of these points, but let's use the given point. 3, 5, -1. And so I can plug these in. Our A would be 8, x minus 3. B would be 5. Sorry, B would be 1. Y minus 5. And the Z, which is a -2, Z plus 1. And that's the equation of your plane here. Oh, they actually multiply this out. Do I? Let's do it just to compare. So this is 8x minus 24, I want to say, plus y minus 5 minus 2z minus 2 equals 0. So this is 8x plus y minus 2z minus 24 minus 5 is minus 29. Minus 2 is minus 31. Bring it over the other side, you get 31. And that looks like this guy right here. All right, so that's awesome. That's planes. And you should know pretty much, so this is some common situations that you would find. So the idea though is you should be able to know the equation of a plane, know the equation of a line, and be able to find equations of planes and equations of lines from various situations. So for a line, I can give you a direction and a point, or I can give you 2 points, or I can give you something else. I can say, oh, find the equation of the line that passes through this point that is perpendicular to this plane over here. You should be able to figure that out. Or you can describe all sorts of things in 3 dimensions. Another common thing to ask about is something like, well, we know 2 planes intersect. Find the equation for their line of intersection. So something like the line that goes here. So it's called the line of intersection. And there are problems that will ask you to find that. And the trick, of course, is to realize that that direction is actually the cross product of the 2 normal vectors. And I'll leave you guys to think about why that is the case. So situations like this will arise. You need to know equations of lines and planes and how to find them in various situations. And very common thing to ask about, almost sure you're going to be asking, I'm definitely going to ask you about questions like these in my test. How the final should ask you about them, although I don't know in what variation. But it might give you like, describe a situation, and it'll write down several versions of a plane maybe that you have to choose from. I don't really know. But if the final is going to be Blackboard, I'm assuming it's going to be a lot of short answer, multiple choice, matching stuff, that kind of thing. But yeah, your textbook will have a lot more problems like this, and you'll see problems like this in your homework. But you really need to know about equations of lines and planes and just figuring out how to do them, how to construct an equation that satisfies some properties. Similar to the things you did back in pre-calc when you learned about the equation of a line or the equation of a circle. Find a circle with this center and that, right? You need to get that comfortable with these objects here. So equations of lines and planes, this is the scalar equation of a plane. That's the one you want to remember. For equations of lines, you want to remember the parametric form and the vector form. And the nice thing about these is that these guys generalize very nicely. If we go now into 4 dimensions, there's just another thing like this that's added, right? So there might be a plus d times w minus w naught or whatever. And if in the equations of lines case, if I go into 4 dimensions, the only thing that changes now is now I have a 4th coordinate. But otherwise, everything is going to look the same. So once you actually learn this way to actually write down lines and planes, this will go with you forever, right? You won't have another shock of realizing that you kind of learned something now that you have to totally unlearn. Yeah, so there's that. All right. Let's talk about distances. This is going to be important in a multitude of applications, of course, when you want to find distances between certain objects. But 2 specific instances that you should know about is how to find distances between a point and a line, and distances between a point and a plane, and how you can actually talk about these guys. Now, I'm going to give you equations here. Let's talk about where they come from, and then we are going to do some examples. All right. So suppose I have a line doing its thing. I always forget when I have one of these other colors. Here's a line doing its thing. Here's a point over here, P. So now this line, I would know the vector in the direction of the line, right? So it'll be some point here, and I will know that vector. Okay. So let's say this is some point on the line. And we'll have the equation of a line, so I'll know how to find that point. What we would do is I would connect this point to the point over here. And what we want to do is we want to measure the perpendicular distance from the line here, D. We want to somehow measure that. Now, here's how we're going to look at things. We are going to look at this as if it were a right triangle. Let's suppose I know that. Let's suppose I know this here. Let's suppose I know the direction vector for the line, which I would know if I know the equation. I have all of these things here. What is actually the distance D? Well, the distance D is going to be equal to, by trigonometry, magnitude of B sine theta. And what can you do with that? Well, this is like having the magnitude of B. So D is equal to magnitude of B sine theta. What you can do is you can multiply and divide by the magnitude of A, right? As long as it's not the 0 vector, which it wouldn't be a line if there was a 0 vector there. And this part here, you'll notice what that is, at least you should remember, that is the magnitude of the cross product. So it turns out I can find the distance between a point and a line using the magnitude of a cross product. And in fact, that's the equation that we have here. Okay, so let D be the distance between a point P and a line with direction vector A. Then D can be given by this expression, where B is a vector from the line to the point. Pick any random point on the line, attach a vector from that point to from the point P to the line. That's your vector B. Do the cross product of A and divide by the magnitude of A. That's the distance. All right. Now let's actually look at point to a plane. So this is another scenario that, and then we'll do some examples. And then we'll go into something else a little bit, which I think is cool. So here's a plane. Here's my point over here. And again, we want to measure the distance from this point to the plane here, the perpendicular distance. So this is D. Here's how you would do it in the case of a plane. Again, pick a random point in the plane, which you would know if you had the equation. So this is just some random point, x naught, y naught, z naught. And create a vector that hits P. Boom. I'm again going to call that B. Now, at the same time, let's look at the normal vector, because that is going to be perpendicular running up. And now what you can notice, how I can look at D, is if I project the shadow onto this vector over here and then find the scalar projection, that is going to allow me to find the distance. So one thing you'll notice here is that D is going to be equal to the scalar projection, which we call component of B, project its shadow onto N. Now, in general, you can have signs here. So what we normally do is just, we consider it absolute value. We want to think of it as the distance is positive. So it's the positive component of B onto N, which we know is N dot B over the magnitude of N. And that leads us to this formula over here. Okay. So with these two formulas, I can find the distance between points and lines and the distance between points and planes. Let's actually do some examples. Let's celebrate our newfound knowledge by doing some examples. So for example, suppose I want to find the distance from the point 1, 1, 1 to this line. And I put the answer in here because, you know, I wasn't sure if I would get through everything, but we are going to get through everything. This is the last thing in this section. Okay, so let me sip on my tea here. All right, so what we would do is we would find, so here's a point P, 1, 1, 1. Here's the line. This is the line x, y, z equals 0, 6, 8 plus t times -1, -2, -1. Okay, so I'm going to pick a random point. So call this point 0, 6, 8. So that's when I plug in t equals 0. I will connect the vector to the point P. That's going to be my B. So here, my B is going to be equal to 1 minus 0, 1 minus 6, and 1 minus 8. And at the same time, my A is the direction vector for the line. So this is -1, -2, -1. Then what I'm going to do is I'm going to find the cross product. I, J, K. And at this point, you guys have probably gotten a lot of practice with the cross products by doing the homeworks. So this is going to be 14 minus 5. I want to say so that's 9. This is going to be 7 plus 1. It's going to be 8, but then you make that negative. And blocking this out, this is going to be 5 plus 2. That's going to be 7. Then you're going to want to find the magnitude of the cross product. This is the square root of 9 squared plus 8 squared plus 7 squared. Then you're going to want to find the magnitude of A. Now A was, this is going to be 4 plus 1 plus 1, so that's radical 6. And so the distance is going to be A cross B, magnitude over the magnitude of A. And that is going to be the radical of 9 squared plus 8 squared plus 7 squared over radical 6. And that should simplify to 97 over 3. Do we want to do this? 81 plus 64 plus 40. I mean, you can do it. I'm not going to. I just really can't be bothered at this point. Okay. Another thing, let's actually look at this. Find the distance between a point and a plane. So again, here's a plane. Now, to solve these problems, you don't have to draw the picture. You can just know the formulas. So here's the point 2, 8, 4. A point in the plane, and I need the normal vector. So I know the normal vector already. That's 2, 1, 1. Pick a random point in the plane. Now, any point in the plane. So I just have to come up with combinations of x, y, and z that will give me 5. So what I could do here is like a 1, a 2, and a 1. And that'll work. That'll give me 4 plus 1, which is a 5. So I'll just pick that random point here. 1, 2, 1. And then connect that. That will give me B. So now my B is final minus initial. 2 minus 1, 8 minus 2, 4 minus 1. And my N is that. So this means that my distance D is going to be the magnitude of the component of B onto N. And so what that's going to be, that is going to be the absolute values of N dot B divided by magnitude of N. N dot B, 2 plus 6 plus 3. And the magnitude of N, 4 plus 1 plus 1, that's radical 6. And that's already positive. So this is going to be 8 plus 3, that's 11 over radical 6. And that's a little bit nicer. Yeah, so that's the answer there. All right, so that's how we can find the distance from a point to a plane or a point to a line. But yeah, that is, oh, Asha's helping me out there with the 194. I just saw it. So this is like 194 over 6, and then 194 divided by 2 should give you 97. Yeah. So this would be 194 over radical 6. Then take 2 into this goes 3, 2 into that goes 97. Okay. All right, so that ends this section. Now we know about equations of lines and planes, as well as how to find distances. Now, what I want to do is talk about one of the things in the next section. So we'll start this one now. Cylinders and quadric surfaces. It will be very important for you to know how to sketch a variety of objects in 3 space. So the same way that sketching can actually help you out a lot in Calc 1 and previous classes, knowing how to sketch different kinds of surfaces is going to be important. So I showed you how to sketch a plane, you should know how to sketch a line. know how to sketch a vector to some degree, because positional awareness is going to be very, very important. There are going to be times in the future when you're going to be described, a region is going to be described to you. That's like a combination of different regions. Oh, there's this surface over here, and then there's that surface, and there's a plane slicing across this. You have to kind of put these all together and sketch an object. And that's because positional awareness is going to be important. So you're going to want to know which surface is on top of which one is to the right of this, what is to the left of that, who's underneath. Like if they intersect, what is the curve of intersection? If I were to shine a light this way and project a shadow over there, what is that going to look like? You're going to need a lot of spatial awareness to do multivariable calculus, and in Calc 3. It is going to be muy importante. Now, we are going to show you how to, and by we, I mean the royal we, it's just me over here, how to sketch some of these guys. So I'm going to show you how to sketch cylinders and quadric surfaces. Now, a cylinder, and I have some technical definitions written down here, but I don't want to get bogged down in that. But what do you want to think of it? A cylinder is just a curve propagated along an axis. So you start out with a curve, right? So let's say I have like this curve. Okay, now I choose an axis and I just move that curve along the axis. So I can actually move this curve, say parallel to some axis here, right? So, and then it's like I'm just sliding it along. Now it will create a two-dimensional shape. Right? That two-dimensional shape is what we call a cylinder. Okay? So it's just a curve being propagated along an axis. So you can actually just imagine that there's an invisible axis that's here. Right? So you're moving this curve, extending it along an axis. And so you can take a one-dimensional thing, which is a curve, and you can extend it into a two-dimensional thing. Now, as long as you keep moving parallel, such that any slice that is orthogonal to the axis, so you want to slice across here, every time you make a slice orthogonal to the axis, you get the same curve, right? So all along, you will have the same curve. A slice at any point is going to give you that same curve over and over and over again, running along the curve. Now, what that gives you is objects like this, okay? So here we have something like a parabolic cylinder. Here there's a circular cylinder. Here there's a hyperbolic cylinder, okay? And what you'll notice is it's always the same curve. So over here, it's like there's always a parabola, right? So there's a parabola. If I move down a little bit further, here's the parabola again. Here's the parabola again, right? It's always the same parabola. Notice that this is moving along an axis, namely the y-axis is the axis that it's moving along. Here, if I were to slice, I would see a circle. And slice down here, I would see the same circle. Slice down here, I would see the same circle. Slice here, see the same circle. It's always a circle. As long as I'm moving along this axis and I slice perpendicular to it, I'll always see a same circle. This is a circular cylinder. Similarly here, as long as I'm moving along this axis, every time I slice, use a different color here because it's already red, it will look like a hyperbola. Right? All the slices are hyperbolas, hence this is called a hyperbolic cylinder. So all the slices here, they look like hyperbolas like that, right? Where my y is here, my z is here, which of course you need to remember your conic sections for that. And over here, this one just looks like a circle when I'm looking at my x and my y. And of course, this one here looks like a parabola. When I'm looking at z and x, I'm seeing parabolas that looks like that. So I just take this curve and I extend it along the y-axis, and the result is a parabolic cylinder. If I take a circle, extend it along the z-axis, a circle that is in the xy plane, say, that will create a circular cylinder. It's a 2D figure and it's hollow. So these are two-dimensional surfaces. Well, the surface is always going to be two dimensions. These are two-dimensional figures such that they have the same cross section once you're slicing perpendicular to some axis, and you're just having that one shape being propagated along an axis. This gives rise to something that's called a cylinder. Now, hopefully that gives you some appreciation of what a cylinder is. How do you recognize a cylinder is the important thing. So if you have a random equation on paper, how do you know the thing you're looking at is a cylinder? And how do you even go about sketching it or drawing it or understanding what it means? Okay, so here's the thing. In 3 space, and the only exception to what I'm about to say is planes that only have like one variable. Like we know that x equals 1 is a plane, or y equals 5 is a plane, or z equals 4 is a plane. And a plane is also a weird kind of a cylinder. It's like if you have a straight line propagated along an axis, you get a plane. Okay, so for all non-planar cylinders, this is going to be true. The equation will have only 2 of the variables. So for example, if I look at x squared plus y squared, y equals x squared, okay? Notice that there are 3 variables, x, y, and z. Only 2 of them are present. That is a cylinder. If I have x squared plus z squared equals 1, that is a cylinder. Why? The y is missing. Y equals x squared is a cylinder. Why? The z is missing. The equation of a cylinder will have 1 variable missing as long as it's not a plane. Okay? That is how you're going to know. So once you see something like that, it is a cylinder, right? 2 variables only in the equation, it's a cylinder. Now, the missing variable gives you the axis. So for example, if I'm looking at y equals x squared, what that means is that the axis is parallel to the z-axis. So if I look at y equals x squared, I know that this is what it looks like in the xy. Then what that looks like in 3 space is basically y equals x squared is this parabola here on the floor, and that's being extended along the y-axis. Okay. So if I look at, say, x squared plus z squared equals 1, the y is missing. That tells me this is a cylinder, and it tells me that this is an object being stretched along the y-axis. So x squared plus y squared equals 1 is a circle of radius 1 centered at the origin. So this is another circular cylinder. If I look at this guy, this is not a cylinder. How do I know it's not a cylinder? All 3 variables are present. The x squared, x is there, y is there, and z is there. So one way you can know a non-planar cylinder whenever you're looking at it is just to look at how many variables are in the equation. If you have 1 missing variable, it is a cylinder. If you don't, it's not a cylinder, right? And like I said, the only exception to this are planes, right? So let's actually do an example and talk about how you would sketch a cylinder, okay? Now, the curve that creates the cylinder, the one that you would see all the time if you slice it cross-sectionally, this is called the generating curve. And when it comes to sketching cylinders, what you first want to do is you first want to sketch the generating curve. So here, this is the equation of a cylinder. How do I know? The y is missing. So given that the y is missing, I still want to find the generating curve. That's how I'm going to be able to sketch it. Okay, so let's see who's been paying attention. What kind of a curve is that? What kind of curve is that? Well, cylinder is the surface. Think of this in 2D. I'm sketching the curve, right? So let's say I'm sketching in the XZ plane, right? So the actual curve, what is that? X squared over 9 plus Z squared equals 1. What is it? It's not a parabola. Okay, it's an ellipse, right? So remember way back when we covered conic sections? Yeah, all that stuff, you're gonna remember that stuff, right? So that is the equation of a hyperbola. If it has a negative sign in it, if it has a positive sign, it is an ellipse if the denominators are different. When the denominators are the same, you get a circle, which is over here. So what we are looking at is an ellipse. The center is the origin. The bottom is 3 squared, which means you stretch 3 units in the x, left and right. You stretch 1 unit in the z, up and down. And then you actually connect these. Let's keep it red. You connect these with a curve, and that curve is an ellipse. Now you go and you move to 3 space. And you want to sketch this guy. What does that look like in 3 space now? So now we know it's a cylinder because it has only 2 variables present. But what is it going to look like? Well, the generating curve is an ellipse, and it is in the xz plane. So it's like this guy stretching here. And so now what we're do is we run that curve along the y-axis. Right? So at every point, if you slice it, you will see this ellipse. Right? And then it runs forever in both directions. So it's it looks like this, but it's like a little squished circle, and it's running along the y-axis, right? So that would be the picture. Okay, so now that's pretty much all you need to know for cylinders, what they are, how you can recognize one when you're looking at the equation, and how to actually sketch it. Other than that, there's an infinite variety of cylinders that are out there. I can't really tell you a general process for all of them. You just have to be able to recognize whatever curve you're currently looking at, identify it as something you know before, like it's a line, or it's a parabola, or it's a ellipse, or it's a hyperbola, or it's something. And then you extend it along an axis. Next time, we're going to look at sketching some more really neat things. The quadric surfaces. Just had a brain freeze just now. So next time we'll look into sketching these, but we're going to wrap up there for now. So, which, you know, I've been setting up a lot of tests, didn't get a lot of sleep. Anyway, let's move on. That's where we're gonna stop. We will move on to quadric surfaces next time, which is Friday at some point, which I'll send out the doodle so we can do it. But sketching these guys is important. We'll talk more about it next time. That's how we sketch cylinders. And also we looked at the equations of lines and planes. You need to know 2 equations of lines, 1 equation of a plane. You need to know how to construct the equation of a line or a plane given sufficient data. You need to know how to sketch a cylinder, how to recognize you're looking at the equation of a cylinder, and how to recognize what axis the cylinder has. Those are all going to be very important moving forward. And for now, we'll just wrap up there. Yeah, that being said, I am going to open the mock test again. I'll leave it open until, I don't know, I guess Thursday around noonish, make sure everyone actually gets a chance. But of course, I would highly recommend that you try to get it out of the way sooner rather than later. So if you realize that there's something you need to fix, if you realize your computer doesn't have enough memory, you need to free up some space, or you need to borrow someone's laptop or something, like you have time to actually get all that stuff to work out. So I would say do that sooner rather than later, and make sure you actually know how to use the online platform to take the test.
Oh,
yes.
I have 2 questions. So the first one is on your email, you send a app for scanning, right?
Yes.
So but for the iPhone, there is a way you can scan your documents without downloading that app. So can I, instead of doing that, and upload it?
What is the way?
for the iPhone, when you go to Notes, there is gonna be a plus sign, and when you press on the plus sign, it says that do you want to scan any document, and you can scan anything, and you can save it there.
Okay, all right, that's cool.
And for the second,
I don't. Those were just apps that I read would work very nicely. But if your iPhone has a built-in feature, that's also fine. Whatever you do, just make sure you can scan and upload it within like a 10-minute window. You should be able to scan a bunch of pages in a certain order and upload it to somewhere. So as long as whatever you're doing can be done that quickly, I don't particularly care how you scan it. But for people who don't have a scanner and they don't have a phone with a built-in app, I would use one of those two things. But yeah.
And for the second question, do you actually need the camera? Because my camera is like a little broken, but I'm not sure if it's gonna work or not.
Yes, you would need to somehow get a webcam bar or something, or I don't know. But you'll need it requires a webcam.
Oh, okay. All right.
Yeah, so get to work on that. Yes, there'll be a timer during the test. So the reason why you might not have seen a timer if you practice this time around is because I left like a wide open window. It was like there was like a 24-hour plus window left open. But the test is going to be like an hour and a half, so you'll actually see the clock counting down. So you shouldn't run out of time. So pretty much the protocol is going to be something like, I'm going to open the test like 15 minutes early. So while our test would technically officially start at 4, I'll open it around 3:45, just so that if you're in a situation where you might have to restart your browser or restart your computer or something, you have that little cushion right there. The test will continue for an hour and a half. So it'll go from like 4 to 5:30 officially, even though you can get in 15 minutes early. And then at 5:30, you're going to be kicked out of the test, and then you have until 5:40 to upload your scans. Okay, so in terms of the timing, that's kind of how you want to think it's going to happen. So you have a little cushion for those of you who just, there were people who couldn't get certain things to load. I want you guys to try again. There were people who got things to load, but they said it took them, their computer, like 10 minutes to load or something. So if you know that by practicing the mock test, that's good. You good that you know now as opposed to test day. So just show up like 10, 15 minutes early and start loading, right? And then by the time 4 o'clock comes around, you should be starting or already started. Okay. All right, but do what you can to get everything to run as smoothly as possible. You really want to have things clean and streamlined. And yeah, for now, we'll end there. And I will see you guys on Thursday. So, ciao, I guess, is all.
Wait, Professor, or do you have to join in the Zoom meeting on Thursday or no?
No, you would go straight there.
Oh, okay.
So, I'll probably have Zoom open just in case anyone has to reach out for me, but it's an emergency. Zoom shouldn't be the main thing.
So what if there's we have like any question or something, how can we ask?
I think there's probably a feature inside to it. I'll be around, so.
Okay. So if I email you, you're gonna see it, right?
Yeah.
Okay.
All right. Good night. Stay safe, everyone. I will see you guys in the next one. Take care.